It's like, well, I mean, part of it is like being I need to make decisions. The best thing always. Yeah, so much more. I start to like I don't think anything. I never think we get into the
Hi everybody, welcome. Thanks for coming. Nice to have such a full house here, and hello to folks who are watching online. It's really a pleasure to be introducing Lizzy Kysela. Lizzy has been a student working with me for about 5 years. Lizzy was an undergrad here at the University of Wisconsin-Madison, majoring in environmental sciences with a certificate in food systems. Then she worked for an intern, as a full-time intern for a year, and is now finishing her master's here in the Department of Atmospheric and Oceanic Sciences. And I think you'll be impressed with all the work that Lizzy has done. So I will hand the floor to her. But first, I'll remind everybody of the terms of the meeting. Is that questions during the talk should be just for clarification, like reading a legend or something like that. Then when Lizzy finishes, we'll have questions from the audience. And then after that, we'll have questions from her committee, Brad Pierce and Myra Oyola Merced. So we'll go into closed session later. Thanks everyone for coming, and thank you, Lizzy. Take it away.
Thank you everyone so much for coming, and thank you Tracy for that introduction. Today I'll be presenting on sectoral emissions contributions to annual fine particulate matter at urban to regional scales. And so I'll start off with a little bit more about me. Like Tracy said, I'm actually from Cleveland, Ohio, and thank you to my brother for providing this lovely shot of Cleveland. I feel like it really paints a picture of, you can see sort of, there's a smokestack here, there's a smokestack there, there's sort of piles of uncovered industrial materials, and you can also see this river running through Cleveland called the Cuyahoga River, which is famous for catching on fire. That's not a joke. In fact, it was heavily polluted, and there was an oil slick on top, and so actually first responders had a very difficult time putting out that fire. And that occurred in 1969. It was sort of a national news event. The last told story is that it did in fact happen 13 times. And so I love this picture because I feel like it paints the fact that Cleveland is built on industry. And it's an integral part of the culture of the city. I feel like it really encapsulates sort of industry in the foreground that built that beautiful skyline. And so coming from Cleveland and now working in air pollution, I do have a little bit of a different view on it, sort of retroactively, of understanding all of the different sources that were happening within the city. But I will also say that I love Cleveland and I love the people there, and so this has been a really interesting journey. And so I moved to Madison actually in 2018, and I did my Bachelor's of Science in Environmental Sciences, and I loved it. I feel like I got exposure to a lot of different topics, and that's how I started working with Tracy. And along with that, I also felt like I was using these air pollution models and different satellite data, and I felt like I really wanted to drill down on more of the background. I think that was the piece that I was missing, which is what really drove me into atmospheric science, to build a deeper understanding. And so I started working with Tracy on air pollution, and right off the bat, I'd love to thank my funding and collaborators, starting with my advisor, Professor Tracy Holloway, as well as my committee members, Professors Myra Oyela-Merced and Brad Pierce. I'd also like to thank NASA, the McKnight Foundation, Audi Settlement Funds, and the American Lung Association that made this work possible. I'd like to thank collaborators that were formerly at UW-Madison, Roy Wang and Chandler Wells, as well as collaborators at University of Illinois Urbana-Champaign, Professors Chris Tessum, Dr. Hamida Manupur, and Xiao Ran. And so with that, I'd like to give a little context of following my undergraduate degree. As Tracy said, I did an internship with the Holloway Group. And this was focusing on community engagement and engaged research with organizations focused on equity and health at the national to local scale. And so I got to work on really cool projects with organizations like the Wisconsin Asthma Coalition, and they focus on childhood asthma in Milwaukee, and specifically children of color with higher asthma incidence and emergency department rates within Milwaukee, as well as the MKE Fresh Air Collective, which was founded by Langston Burdett in Milwaukee, that single-handedly built a low-cost sensor network and is now working to provide alerts to people when there's high air pollution local to them. And so working with some of these groups, as well as Breathe Providence, which is another low-cost sensor network out of Rhode Island. And as a graduate student, I also got to work as part of an energy analysis and policy capstone group to work with the city of Madison on the low-cost sensors they're installing now. And so through this, I found a real passion for working with organizations and understanding community information needs. And during my thesis, I also had the opportunity to work with the American Lung Association, sort of highlighted here, the first of two Something in the Air reports that came out of the work with our group. And it was used satellite-derived data and satellite data in new ways, in ways that are interesting to the community health groups, in understanding sort of census tract area averaged, and more applicable ways to use satellite data. And so let's talk a little bit more about the satellite-derived data. This is out of the Atmospheric Composition Group, Atmospheric Analysis Composition Group at Washington University. Here I show some of the performance of this data, and so I'll show sort of the x-axes are the monitor data coming from the EPA's network of ground-based regulatory grade monitors. The y-axes are the satellite-derived data, and the red line is a one-to-one line. And so above the line is overestimation, and below the line is underestimation. And so we can gather from these plots that we see good performance from the satellite-derived data, and the reason it's called satellite-derived data is because it's a data fusion product that uses both satellite observations as well as a chemical transport model, GEOS-CAD, and some of the ground-based monitors as well to create this continuous spatial coverage data product. And the spatial coverage is a big part, especially for understanding exposure. Many counties are unmonitored for air pollution. However, to understand intra-county exposure, you need sort of that spatial coverage. And so that's really the strength of this satellite-derived data, is the good performance and full coverage. However, this doesn't tell you that much up front about where the air pollution is coming from. And a lot of times community groups would be very interested in, I know I have bad air, I breathe it every day, but where is it coming from? And so this is really what motivated this project. Where is the ambient pollution coming from, and who is most affected by it? And so with that, we'll sort of jump into the methodology of this project. And the first step was gathering emissions inputs. And these will be annual emissions, and they're spatially allocated. And so we include 15 emission source sectors here from 3 emission inventories on the right. And I'll go through these, but the first one is the National Emissions Inventory Modeling Platform. This is for the year 2017. And for this emissions inventory, we source airports, agricultural fires, which includes both prescribed burns and wildfires, point oil and gas production, electricity generation, and industry. And the important part of this emissions inventory is some of these sources also require stack characteristic information, like stack height, diameter, temperature, velocity. They're sort of elevated source characteristics that are necessary for the model. The second inventory that we use is from the Texas Commission on Environmental Quality, and it's actually results from the biogenic emissions inventory system, version 3.7, in which they produce biogenic volatile organic compounds. And to give a quick definition on that, these are VOCs that are emitted by plant vegetation as a natural process. And if you're thinking to yourself, why the Texas Commission on Environmental Quality? That is because it's difficult to find biogenic emissions inputs for more complicated models, like the Community Multi-Scale Air Quality Model, or CMAC. This would be calculated in line. However, we're using a very simple model later in this presentation that does not have any inline calculations. And so, luckily, some of the bigger air quality management districts, departments like TCEQ, are required to make their modeling publicly available. And so we use those emissions as an input here for the biogenics. And so the final emissions inventory is the Neighborhood Emissions Mapping Operation, or NEMO. And again, this is for year 2017. And this is a project that's out of George Mason University that is focused on taking emissions at the national scale and allocating them to a very fine resolution. And so the strength of this emissions inventory is that it's down to 1 by 1 kilometers, which is very fine. And so this is for the sectors of agriculture, area fugitive dust, which includes things like construction, demolition, as well as roadway dust. Then we also have the non-point sector, which includes all things that are too small individually to be considered point sources, but together they make up an entire category. And so this includes everything from residential heating to consumer solvent use. It's a very broad category. Next, we have non-road vehicles, and this includes vehicles like ATVs, off-roading equipment, farm equipment, things you wouldn't necessarily see on the highway. Then we have non-point oil and gas production, followed by on-road vehicles, which includes everything from light-duty passenger cars all the way up to semi-trucks. We also have rail emissions and emissions from residential wood combustion. And the reason that we don't only use the neighborhood emissions mapping operation emissions is that it doesn't have any elevated sources. And so we've had to sort of combine multiple different sources of data to give a full picture. And so now let's look at sort of the geographic distribution of a few of these sources. And so we have primary fine particulate matter in green, sulfur oxides in yellow, ammonia in this teal color, nitrogen oxides in red, and VOCs in navy. And they're plotted in this order, so VOCs are on top. So here we see fires, which again are prescribed burns and wildfires. And we see a higher density of emissions here in the southeast, as well as along the west, with some in Michigan as well. We can also look at, oh, and yes, and the size of the circles indicate the magnitude of the emissions. We can also look at the electricity generation sector. And so this is a sector known for producing more nitrogen oxides and sulfur oxides. And there's also the historical context of a heavy density of coal power plants located in the Ohio River Valley region, which is right in here. However, we have seen some move from coal as well as controls and regulations placed on these emissions that have helped reduce sulfur oxide emissions in particular as well. We can also look at sectors like agricultural emissions, and so here agriculture emits ammonia and VOCs, and we see the biggest emissions in the Midwest area as well as the San Joaquin Valley area of California over here, and the same for ammonia. And in some ways we can use the input emissions as a clue for understanding where the pollution is coming from. For example, 80% of all of the ammonia in this project is coming from the agricultural sector. And so we can somewhat contextualize our results for the formation from ammonia with which sources are heavily emitting it, but you can't actually conduct source contribution from emissions alone. That's the difference between emissions and what's ambiently in the air. And so now let's talk about biogenic VOCs. Again, these are from plant vegetation. And we're seeing high emissions in the southeast, as well as in parts of California, and less so up north. And this can be a function of plant vegetation type, plant density, as well as things like temperature and humidity. And now that we've sourced our emissions inputs, let's discuss our tools. We use the intervention model for air pollution, or InMAP, combined with satellite data. And so let's talk a little bit more about the model. It's a very interesting model. It's a reduced form or reduced complexity model, and it has this variable grid. And so there are bigger grid cells in rural areas and smaller grid cells in urban areas. And so the way this works is all of the grid cells start at about 288 kilometers by 288 kilometers, and then if the population threshold or the population density threshold is exceeded, it'll divide into smaller and smaller grid cells until it reaches 1 by 1 kilometer. And so here, this is really a way of allocating more computing resources to urban areas and less to rural areas, so that we can understand the higher densities of populations and also higher densities of sources that are occurring in urban areas. So here I show the species that go into InMAP and what comes out. And so on the left, I have volatile organic compounds, or VOCs, nitrogen dioxide, or NO2, sulfur dioxide, SO2, ammonia, NH3, and primary fine particulate matter. On the right, we have secondary organic aerosol, particulate nitrate, particulate sulfate, particulate ammonium, and primary fine particulate matter. And the reason they're connected by a dotted line from the left to the right with the corresponding species is that InMAP is a linear model. And so this is basically saying that the only species used to calculate secondary organic aerosol is volatile organic compounds, and so down the line. This is a really big assumption. InMAP, in some ways, its linear nature is its biggest flaw, and in some ways it's its biggest asset, which we'll see later in the presentation. But this, to be fair, is a big assumption. I worked on a summer REU as an undergraduate, looking at how decreases in SO2 and resulting sulfate formation were actually leading to increased nitrate formation from NO2 in the northeast. And so when we look at the chemistry that's happening, there are nonlinear processes and more complexities that exist that are not captured by this model. And with that, we'll move to sort of the fundamental equation of InMAP before we go too deep on the limitations. This equation starts with the concentration of the pollutant, and then uses the gradient of molecular diffusion, and this is really serving as the dispersion term of this equation. And then we have the gradient of wind vector and concentration, and this is really serving transportation, or transport of pollutants. And then we have the net formation of the pollutant, and this is encompassing the chemistry that's going on. And then we also have the emissions of the pollutant, as well as deposition, so it being deposited out of the air. The variables in this model are defined by model output of the weather research and forecasting model coupled with chemistry at the 12-kilometer resolution for the year 2005, so about 20 years ago. And that's what this model is built from. And so let's now talk about some of our results for 3 of the output species. And so again, on the x-axis we have the monitor data. Here on the y-axis we have the unscaled InMAP results. And we have our red 1-to-1 line. And we see that there's underestimation for particulate sulfate, whereas we find particulate nitrate also has underestimation, but not to the same extent. And then finally we find that particulate ammonium is far overestimating formation of particulate ammonium, and particulate ammonium is performing the worst of the 3 species. And so we see that performance here is not where we want it to be, and we can also discuss why that could be. As we talked about, the linear nature of InMAP simplifies many things. It also simplifies that all sulfur oxides are considered as sulfur dioxide, all nitrogen oxides are considered as nitrogen dioxide, and all VOCs are taken in as one category, which is an oversimplification. There's a lot of different types of VOCs that have different amounts of reactivity. And so in short, the chemistry is simplified, but we're also using a model based on the meteorology of a single year for 2005. And also with that, we're using a model producing an annual average fine particulate matter from annual total emissions. And so you're losing a lot of that sort of day-to-day fluctuations. Finally, we're also using a 12-kilometer run of WRF Chem to produce this model. And I'm saying we, but actually Chris Desson made the model. The model is built from WRF Chem output for at the 12-kilometer scale, but we're making predictions down to the 1 by 1 kilometer. And so these are some of the factors that could be contributing to the poor performance of the model alone. And so here we really see the need for correction in some way. This is where the satellite-derived data comes in. And to start, this is a little bit of an unconventional approach and only made possible by the fact that InMAP is a linear model. And so we can derive scaling factors from the satellite-derived data and then apply these scaling factors to each sector run. And so here we show, on the far left, the unscaled InMAP results for particulate sulfate. In the middle, we show the results for satellite-derived data alone for particulate sulfate. And then on the far right, we show our scaled InMAP results. And the interesting takeaway here is that InMAP alone performs poorly, satellite-derived data performs better, and actually we find that scaled InMAP performs best. We can also look at the other scaled species, like particulate nitrate. And again, on the far left, we see InMAP alone. In the middle, satellite-derived data. And then here we have scaled InMAP. And again, we see sort of worst, better, best from left to right. We can look at our final scaled species, which was the worst performer, particulate ammonium formation. Here on the left, we have the unscaled InMAP with a lot of overestimation. We have our satellite-derived data in the middle here, and then over here we have the scaled InMAP results. And again, we see the best performance from the scaled InMAP results. And our sort of working hypothesis on why this could be is in our other project with the American Lung Association, we found that when we were taking sort of the maximum grid cell in a county or a 90th percentile grid cell in a county, there was more chance of outliers, whereas when we did area averaging, we saw sort of different results. And so part of our improvement here might be a factor of the area averaging that's part of the scaling process. We're also curious, how does this impact the recalculated total fine particulate matter? And so here we have on the far left the InMAP results alone. In the middle we have the scaled InMAP results, and on the far right we have the satellite-derived data alone. And note, to be clear, the total satellite-derived data is not used for scaling here, it's only brought in as a comparison. And so we have InMAP alone here. We have scaled InMAP here, which performs better than an InMAP alone. However, we see the best performance out of satellite-derived data here. And so now we'll talk about the concentrations and what's contributing to this pattern. And so we'll start with this plot that on the x-axis has different regions of the United States, and on the y-axis is the average concentration, and it's shown by species. And so here we see that secondary organic aerosols in pink are the highest output concentration in all regions except the Northwest, making up the largest proportion of the total. And notably, this species does not have analogous satellite-derived data, and so it is not scaled. And so from the left plot here to the right, there will be no difference in secondary organic aerosols. We can also look at primary fine particulate matter, which is the other unscaled species. And we can see that primary fine particulate matter is the second most contributing species, except for in the Northwest, where it is the top species. And again, from the left to the right, there is no change because we are not scaling this species. But we can also dial in on the scaled species specifically and look region by region. And so first we look at particulate sulfate, and remember that we were underestimating the formation. And so from the unscaled results over here to the scaled results, we see an increase in every region. Alternatively, when we look at particulate nitrate, we see that there are some slight regional differences in scaling impacts. And so from the left to the right, we see increases in these four regions circled in red. The Northeast, the Northwest, Southwest, and Midwest. Whereas in the other two regions, we're actually seeing a decrease as a result of scaling. Our final species, particulate ammonium, which we saw a lot of overestimation, now decreases in all regions as a result of scaling. And so now we can look at what this looks like on a national total scale. So now we have maps of fine particulate matter for the US. And over here we have unscaled results, and over here we have our scaled results. And in these areas circled in white, we see decreases as a result of scaling roughly over these areas. So we're seeing decreases in the Colorado area, the South Central, and the North Carolina areas as a result of scaling. Whereas if we look at some of the cities across the US, we see increases as a result of scaling. And so looking at Los Angeles and Salt Lake City, the Chicago, Milwaukee area, Cleveland and Detroit, and then over here in New York, we're actually seeing increases from the left plot to the right plot. And so now we have our concentrations, we've talked about it, and now we'll move to look at source contribution. And so where are sources contributing the most? We'll start with this map where we show the proportion of which each sector contributes to the total fine particulate matter. And so one would be the whole of the concentration, and so this is sort of the fraction for each sector. And so here for fires, which again is prescribed burns and wildfires together, we see the highest fractional contributions in the Northwest, as well as in the the central United States, and then some in the southeast. Whereas if we look at a sector like the biogenics, we see high fractional contributions in the southeast, in the southwest, and interestingly, where we saw higher emissions in California, we don't see corresponding high fractional contribution. You can also tell from this map where some urban areas are. There's the absence of a high fractional contribution in some of the urban areas across the United States, like here in Minneapolis or Chicago. I think also this slide emphasizes the importance of including biogenic VOC emissions, even when using a simpler reduced form model like the one we're using. We can also look at sectors like the non-point oil and gas, which is a very high contributing sector through the central part of the country, especially in areas of Colorado and then down through Texas as well. A little bit over here, sort of in the northeast, although to a lesser extent, as well as up here in North Dakota. Finally, we chose one more sector to highlight the results. The non-point sector. Again, this was the very broad sector that included a lot of little sources. And we see higher fractional contributions in urban areas sprinkled throughout the US, as well as in the Northeast. And this includes things like residential heating or solvent use. There's a lot of things that fit within this category. Now we present this map of the top contributing sector by grid cell. And so interestingly, we find that biogenics are a top source for much of the South, but also some of the northern areas. But we also make the argument that to some extent biogenics are out of human control. And so we do also present a map renormalized without the biogenic contributions. And here we can see that fires are a dominant source in the west as well as in the southeast. And we see that non-point oil and gas is a bigger contributing sector here in the central US, slightly up here in North Dakota, and also sprinkled throughout a little bit of the northeast. We also find that area fugitive dust is a top sector for the upper Midwest. Again, this was construction and demolition and roadway dust. We see that industry is a big contributing sector in the lower Midwest as well as parts of the Southeast. And then we see that electricity generation is a bigger contributing sector here in the Northeast. We also have non-point in the Northeast as a top contributing sector, as well as in urban areas throughout the country. And now we've looked at source contribution. We could also look at health impacts using these results, but this is outside the scope of this work. And so we jump to our final section on environmental justice. And so first, an introduction on environmental justice as a topic. Policies and systemic racism have resulted in disproportionate air pollution burden for communities of color, especially communities with predominantly Black people. And this corresponds also to disproportionate health outcomes. And so one of these policies is called redlining. And so here on the left we have the historical redlining map for Cleveland, where I'm from. And this was a policy where there was refusal of federal home loans in areas marked as high risk, with the area's highest risk in red. And the important thing to understand is the high risk areas were actually just where people of color lived. And so in actuality, these redlined areas were then financially oppressed in a way that also perpetuated racial residential segregation. And this opened the door to things like disproportionate industrial siting, food deserts, also known as food apartheids, and other environmental health justice and environmental health risks. And so this policy, I think, is important to also note. This policy did not end until 1968. And so also on the right here, I've provided the scaled total fine particulate matter results, also for Cleveland, as a side-by-side comparison. We also know that the Highway Act of 1956, the execution of which explicitly targeted communities of color to build roads through. And so that was also adding to the increased emissions of traffic-related air pollution. And so, as a result of these policies and others, people of color in this country breathe more air pollution and have higher health air pollution burdens. And so, I'd also like to say, if you'd like to read more, I highly recommend my colleague's thesis, CC Worth, recently wrote her thesis, and I feel like there's a lot of good background information there. And so now we connect this historical and political context to our results. And so we find that to total fine particulate matter, there's a pattern of overexposure for people of color across US cities. And to explain this diagram a little bit, on the x-axis we have different demographic groups. On the y-axis we have relative exposure disparity. And here people of color is defined as all people that are not non-Hispanic white, and so it is a broad categorization. And relative exposure disparity, when it's positive, indicates an overexposure, whereas when it's negative, it indicates an underexposure. And this is relative to the total population-weighted concentration, which within each city. And so here in these box plots, we also see that the median relative exposure disparity is this black line. And I've also pulled out the actual median relative exposure disparities above each box plot. And so here we find that 94% of the cities that we looked at showed evidence of inequitable exposure to air pollution for people of color. We also find here that non-Hispanic white people have the lowest relative exposure disparity, and Black people have the highest median relative exposure disparity. We can also look within specific cities. And so here we pull out the cities with the 5 highest relative exposure disparities for people of color in the United States. And so we find that the first most inequitable is Providence, Rhode Island, followed by Louisville, Boston, Grand Rapids, and Albany. And you can also see how this, there's a nuanced picture of different demographic groups breathing different air within the same city. And so for Providence, the topmost inequitable city, we can also then extend our fractional contribution to understand what people are breathing. And so here in Providence, we find that the highest contributing sector is the non-point sector, followed by on-road and electricity generation, which are top sources in Providence. And so we can also extend these results to examine equity impacts of individual sectors. And so this is total fine particulate matter that is attributable only to on-road vehicle emissions. And so here we find that 95% of cities that we looked at show evidence of disproportionate exposure for people of color. And we also find that the magnitudes of median relative exposure disparity are greater than total fine particulate matter alone. And we find that non-Hispanic white people have the lowest relative exposure disparity, and that Black people are experiencing the highest median relative exposure disparity. We can also look city by city for the on-road vehicle sector. And again, actually, we find that Providence, Rhode Island is the topmost inequitable city for on-road vehicle emissions, followed by St. Louis, Springfield, Syracuse, and Albany. And again, the further from zero, the more inequitable the exposure to air pollution. And so now we show the source contribution for the second highest city St. Louis, Missouri, since we've already shown Providence. And we see that area fugitive dust and fires are the top contributing sources in St. Louis. We can also look at another sector that's very co-located with urban areas. We found that the non-point sector was the top contributing sector in about half of cities. And so we find that non-point fine particulate matter also shows evidence of a pattern of overexposure for people of color. In fact, we find that 91% of cities show inequity. And so we continue to find that non-Hispanic white people have the lowest median relative exposure disparity, whereas Black people have the highest. And again, I want to emphasize that these are the highest magnitudes yet that we've seen today. And so when we look at individual cities, we are now expanding all the way out to 50% relative exposure disparity. And so here are the top 5 most inequitable exposure cities are Rochester, Lancaster, Pittsburgh, Louisville, and Syracuse. And we can also look at what the what the top most inequitable city for non-point sector emissions looks like in a source contribution. And so here we see that actually the non-point sector is the top contributing sector here. And with this, we find, we then also want to start wrapping up a bit. And the work that I've presented today thus far, and also related work, I'll be working on finalizing for submission this summer. The work with the American Lung Association is in review at PNAS, whereas the work that I worked on for my summer research experience is out in the Science of the Total Environment. And then the work that I've done here today on sectoral emissions and also applying InMAP to equity will be coming out this summer. And so I think to sort of pull these ideas together, I think the takeaways are that InMAP has its shortcomings maybe, but it's also the only model that can be used to do this research. It's specifically positioned for environmental justice analysis and providing adequate spatial and temporal resolution in urban areas. And while it has simplifications of chemistry, those simplifications, the linearity of the model, is also what allows us to complete the scaling and allows for the source sector contribution, which is a very difficult thing to do. Otherwise, you have to bring in different tools or chemical transport models or receptor models. You can absolutely read my thesis if you want to know more, but there's a lot of different ways to do source contribution, but nothing that can give you a national look, spatially continuous, looking at all urban areas in the US at one time. It's sort of remarkable what it can do, but it's also a flawed tool, and so taking a balanced perspective on where and when this model can be used, and also understanding that this will never replace chemical transport models and the complex models and like the top of the line modeling, but this may have a place, especially more on the community engaged side of research. And so I also want to touch on this, a bit of a downer, but this is also existing in the context of our political world at the time. The federal government decided to cut all diversity, equity, and inclusion programs at the government, and we saw the EPA announce walking back regulations for air pollution specifically focused on industrial sources. And so I think sort of another important takeaway of this presentation is it's my opinion that this work shows that this is not in the best interests of the American people. And so finally I'll wrap up on a bit of a higher note. I'd like to thank Professor Tracy Holloway, my advisor, along with my committee members Brad Pierce and Myra Oyola Merced. I'd also like to thank NASA, the McKnight Foundation, Audi Settlement Funds, and the American Lung Association for making this work possible. I'd like to thank collaborators here at UW-Madison and University of Illinois Urbana-Champaign. And finally, I'd like to thank some of my colleagues, Summer Aker, Cece, Monica, Jenna, Kara, Nova, also Brandon, who flew in from out of town as a surprise a bit. And then I would like to thank my family and friends, many of which are either in this room or watching from home. And so thank you so much for your time.
Thanks, Lizzy. That was a great presentation. Questions from the audience?
Yeah, it's a really nice analysis. Nice to see that. Have you looked at anything by varying by season? Because the PM2.5 composition is really different in summer and winter. It'd be really interesting to use. And I know the Washington University analysis is available by month too. Have you done that at all?
Unfortunately, InMAP is an annual average model, and so it's actually not possible to look season by season, but I do agree that that would be a good idea.
Yeah, I think the emission sources are really different too, but yeah, it's a limitation.
Yeah, it seems to me like another strength of looking at InMAP compared to other higher fidelity models might be that you have the opportunity to look specifically at non-local sources, because there's a lot of, like, the factory right there is emitting, or the road right there is emitting, we know that it's right there. But then there are places where it might be non-local. So I was wondering if you've tried to isolate the part of the emissions that are non-local in this model and look at where there's more non-local contribution to particulate matter.
You know, that's not something we've looked at here, but that would be very interesting.
Yeah. And then a related question, so you use just 1 year of the work model. Is it easy to replace which year you're using, or? No, okay.
Not that easy, unfortunately.
Yeah, I was thinking it might be nice to see, like, if you could do a bunch of different years, see how natural variability might change where those emissions are coming from. But yeah, that might be a whole project to get that to work.
Absolutely, thank you.
And then maybe I'll just chime in here to say that just replacing the emissions alone was an enormous, enormous task. And I think Lizzy sort of alluded to that with these 3 different inventories from these 3 state-of-the-art projects. But yeah, swapping in the meteorology would be fantastic, but that was something that's really would have to be done at the model development level.
Okay.
It's not
Yeah.
Well, first of all, Lizzy, you're a great speaker. You've done so much great work. I have 2 questions. My first question is on slide 20. Yeah, so if the total PM2.5 wasn't scaled with that satellite data, what scaling factors do you use?
And so the total scaled is reflective of the individual scaled species, particulate, sulfate, nitrate, and ammonium, then added back in with the sulfate, or secondary organic aerosol and primary fine particulate matter. And so the total itself is not scaled, so there are no scaling factors there. It was only the 3 species that had analogous satellite-derived data that were scaled here.
Thank you. My second question was about the upper Midwest. Like the area fugitive dust was like the highest sector, which I found very interesting. But as that's like construction and road dust, strategic communities, roads, as you know, what suggestions would you have for people trying to improve air quality in Wisconsin, Illinois, Minnesota, as construction and roads aren't likely to disappear?
That's a great question. I think that was also something to add maybe a little bit more perspective on. We actually went to the Air and Waste Management Conference in Chicago this past December, and I was very surprised. There was one air manager in specific that just kept driving home the point that we're not looking at dust enough, which was very interesting. I hadn't produced these results quite yet, so I didn't have any context. It was actually validating to then get my results and see, oh, there actually might be evidence of what this air quality manager is looking at. And I think specifically we can't eliminate roads, but we are moving towards electric vehicles, which are not emitting levels of traffic-related air pollution. And so I think there are ways that we can focus in on emissions reductions that would be more equitable, that might not entail getting rid of construction or roads entirely, which might not be as realistic of an approach.
Hi, this is maybe a question that is not appropriate here, but the top 5 cities that you picked on, I noticed, were St. Louis and other places in the Northeast. Do you have a feeling or a comment, and you can pass, on whether that's because of the population weighting, or there's non-white population more east of the Mississippi River, or if it's these are social political issues that should be discussed, researched in other contexts?
Okay, yes, and maybe it's
I mean,
also,
there are no California or Texas cities, for example, that you mentioned.
right. I think I will also mention that there were over 100 cities included in this analysis, and so each 5 that were pulled out were simply the 5 with the highest relative exposure disparity for people of color. And so whether that's more in the Northeast because there's more inequity there, I'm not sure. I will say that the population weighting concentrations do account for sort of how many people in each demographic group there are relative to the total. I'm sorry, did that answer your question?
Absolutely.
Okay.
Great, other questions?
I just want to follow up on Evan's question about the transport of emissions. So the model doesn't consider if there's a power plant in Indiana and the pollution goes to Wisconsin, it doesn't consider that power plant as a source in that grid box in Wisconsin, or it does. I guess that's what I'm a little confused about.
Yeah, thank you. So if that pollution from a power plant is then moving into Wisconsin, that would be considered in the source contribution as electricity generation, but it wouldn't be tagged in any way to say this is from this power plant. However, you might be able to then, if you were specifically looking at one facility, you could do a run with all power plants, and then you could do a run with just that one power plant excluded and see specifically the difference. This was actually done by a former group member, Clara Jackson, who used this model, and so she did this with the Columbia plant here in Wisconsin. So what would happen if this was just shut off entirely? And so there is a way to do that, but we didn't necessarily focus on local versus transport here, but that's something that you could do. Did that answer your question?
Kind of a clarification, then it's a follow-up. So you're using, you do have hourly 12-kilometer winds in chemistry, right? But you're using the 2017 updated emissions, right? So those winds are, they're advecting a much higher resolution emission source around. Is that right? And then, so, but you do have hourly winds that you then composite all those results over the year. Is that right?
I actually believe that InMAP takes sort of an annual average
Of the
winds.
winds? Okay,
Yeah, so when InMAP was built, there was hourly data,
okay.
but Lizzy is not using hourly data because she's just using InMAP. So it went into the construction of the model, but now it's not there. I mean, now we're just using the hourly. The annual average data is what is being used for Lizzy's calculations.
Okay, but you didn't run NMAP, you just scaled it, is that right?
So I did run InMAP for each individual sector
Okay,
using the emissions, and I agree that InMAP is an interesting model. I feel like I've actually gained more perspective on how maybe unique InMAP is after playing around with different models at my time here as a student. And things like, oh, every time you recompile the model or you're changing different things, this is a very different approach where InMAP is a little bit more of a black box, and you give it the emissions inputs, and it gives you the outputs. And so it's really simple, but it's a little bit more, it's a little less changeable, unfortunately. And so to rebuild with the emissions, or sorry, with the meteorology of a different year, you'd have to rebuild the model.
I have a question that's general and for the benefit of the audience. Do you want to talk a little bit more about your satellite-derived data, what's in there, and how did you treat it?
Sure. So the satellite-derived data is a data fusion product that combines the satellite observations from multiple tools, and then GeoSchem, which is a chemical transport model, and some of the ground-based monitors from the EPA network. And then this is out of WashU. Their team has created a spatially continuous data set at 0.01 degree grid cells. And then using that data, we have the annual values for the scaled species. And then we sort of area average that to the InMAP grid. And then we use that to derive the scaling factors for the total scaled species. And then once we have those scaling factors derived, we then apply it to each individual sector.
Part of the reason that I asked that question is because there's a lot of work that goes into that, and I want to make sure that the audience can caught that. Another thing, one more question is on, I think it's figure 8, or sorry, slide 8. We can talk about the risk missile store. So, I'm a little confused with this map, and I'm going to tell you why. This is emissions. This looks like well, I guess it's just emissions, so that will go into the frequency of emissions rather than how much gets emitted.
Right, so this map is showing sort of the distribution, and so each circle is a different size based on the magnitude of the annual emissions of that location. And the VOCs are plotted last, so it's almost a little bit covered by the VOC emissions, but I believe I also provide the totals. I don't have them in this presentation, but for each input pollutant. But this is, I guess the goal of this plot was to show where the fire emissions happening, more so than frequency, showing the rough distribution of where we're seeing more or less fire emissions.
The reason why I'm asking is because I've done similar work with fire-radiated power and different product, but when you do something similar, what you see is a lot of emission, obviously, on the West Coast. And obviously, if you count the number of fires on the east, they're going to be large. You're going to have a larger number because there's more, but the intensity of those fires are larger on the West Coast. So that's why I was a little confused, because these are supposed to also include the magnitude of the emission, and it looks a tad different from what I was expecting.
Okay.
Yeah, we can, and different products, we can talk about that.
You can see big circles on the western
Yes,
US.
yes,
Lots of-
that's true.
Lots of small circles on the
And
southeast.
here, yeah.
Any other questions from the audience? Well, what, oh, yeah.
Sorry,
sure.
just
That's
a
all right.
couple modeling questions. How long does it take to run InMAP, and do you need a supercomputer to run it?
So it depends. When I first started InMAP, I was running on our local computer Linux. I've since moved over to a different computer. But it can take anywhere to 13 hours for one sector. But if there's fewer emissions, it might be as quick as a couple hours. And so this is very different than something like CMAC, which Monica would have a lot more experience with. But those are much, much, much longer runs. Whereas this is more of an annual overview in a pretty quick modeling time.
Good question. Okay, well, let's thank Lizzy. And we'll take about 5 minutes for folks to say Brad, am I right?